Hello, my name is Patrick Michaud, and this is the first in a series of videos I plan to do where I will be exploring servos and testing servos, primarily for use in First Tech Challenge. I had the idea a little over a year ago that I really wanted to understand the servo system better in First Tech Challenge. Servos have always acted a little funny from what I would normally expect, and I never could tell if it's a problem in the control system or something weird about the servos themselves. And so for the past year, I've been brainstorming what kind of a servo test environment I'd like to have. And this is what I have so far. And I've started doing some servo tests that I'm now publishing on the web. The other thing is that with the changes that occurred over the summer of 2024, where First Tech Challenge is now limiting the types of servos that are allowed for use on robots, this has become a really handy testing environment in order to get an idea of the potential legality of servos that we might want to use in First Tech Challenge. So the base of the system, of course, is a Rev control hub. It has software on it for doing various servo tests. Someday I may switch to a microprocessor-based system so that I can get finer resolution in the control signals and in the readings coming from the servo. But for the moment, this seems to work fine. The control hub has a servo port that is tied to a Studica Robotics servo power block. That servo power block gives us the ability to boost the voltage of the servo up to about 6 volts. Here you can see I'm getting 6.16 volts out of the servo power block. I've been trying to find a source where I could get closer to 6 volts because 6 volts is the voltage you're supposed to be testing and rating servos at. But so far, I haven't found anything that gets me much closer to 6 volts that's better than the Studica power block, so I'm using it. The power block is then tied to a GoBuilda servo monitor. This allows you to monitor the PWM signal, the frequency, the voltage, as you see here, and primarily for our purposes, the current draw of the servo that's connected to it. And so that gives us a way to easily see how much current the servo is drawing as we run it through different tests. We take a servo, I'll talk about this servo here in a second, plug it into the power block, and then from there we can load the servo into this jig. This is a 3D printed jig that I made. It has a servo horn that the servo can go into, and that servo horn drives a arm, and that arm is on a rev through bore encoder that is able to report the position of the arm back to the control hub, so the control hub can use that information for measuring position, speed, a variety of other things as we're doing the tests. The arm here is made a certain length so that it can connect to a force gauge. This is a force gauge that I found on Amazon. It's not a super high precision one. It's one that you can find for a little bit, but it has an anvil on the top, and when you press down on the anvil, it's able to tell you how much force is there in a variety of units. Right now, I have this set to kilograms, and so pressing on the anvil causes the amount of force to be registered where we can read it. And when the force gauge is in place, the anvil is placed at 5 centimeters away from the servo horn, so that we can take whatever value is read on the force gauge, multiply by 5, and that gives us the torque in kilogram centimeters if this is measuring kilograms as it is now. And so that becomes an easy way to measure the torque of the servo by how hard it drives this arm into this force gauge. So let's do some tests. For the test that we're going to do to begin with, today I'm going to start with the Axon MAX Plus servo. And I've chosen the Axon MAX because it's a very popular servo. It's been around for a while. It's also one of the higher end servos that's available for use in First Tech Challenge. And it's probably considered to be the strongest and most powerful servo that you can currently get that is still legal for First Tech Challenge after the rule changes that took place this year. So the first thing I'll do is to plug the servo into the tester. And so let me just go ahead and plug that in like so. And then I'm going to tell the servo I have controls where I can make the servo spin to different locations. I'm going to put the servo at its midpoint and then load it into the jig and with the arm set to its midpoint position. And so that's kind of our default starting position for all of the tests is the servo midpoint. Sometimes it takes me a second to get that in. Once this is in the jig, I have a screw system here that tightens the jig down. These servos can be really, really powerful, and so as we're running the stall test, the servo can deform the jig, and that would actually change the results of the test somewhat. So this little screw system here kind of prevents it from doing that because it doesn't have enough force to release the screw. And so let's just begin with a speed test. Um, I'll just do the speed test and then I'll explain it here in a second. So a speed test takes the servo, runs it through its range of motion, and as it goes through the range of motion, it keeps track of every time it crosses a 10-degree boundary and how long and what time that occurred, and then can report the speed out. Servo speeds are typically reported in time per 60 degrees of movement. So that is how fast or how long does it take a servo to move 60 degrees. On this test that I've done here, you can see that this servo performed, just the top line number is that it had a speed of about 0.1148 seconds per 60 degrees. The reporting that is here, first of all, it reports how long it took for each 10 degrees of the sweep. So to go from minus 130 degrees to minus 70 degrees took 0.113 seconds. To go from minus 120 to minus 60 took that. So each of these are 60-degree intervals, and it reports how long it took the servo to do each of those. But we also have a summary top line number, and this is what I found seems to be the most useful. Um, and I like to report them out this way. So I measure the amount of time it took for the servo to go from minus 60 degrees to plus 60 degrees, and then report that as how long per 60 degrees. And so here you can see that for it to travel the 120 degrees from minus 60 to plus 60, it moved at a speed of 0.1148 seconds per 60 degrees. And then for servos that have extended travel, I'll also report the minus 90 to plus 90 value. And here you can see that in moving from minus 90 to plus 90, the servo moved the velocity or rotational velocity was about 0.1145 seconds per 60 degrees. So if you truncate that to 3 digits, then you would see that this servo moves at about 0.115 seconds per 60 degrees, which is exactly what is mentioned and advertised on the Axon website. So that indicates that the servo and the tester seem to be in alignment in terms of overall speed of the servo. Next, let's do a force test. So in the force test, and I'm going to move the arm here a little bit. In the force test, measuring stall torque has turned out to be really interesting to understand what servos are doing, and explain some other things that I've seen in First Tech Challenge in using servos over many years. So I'm going to go ahead and put the force gauge in place, or I'm going to try and get it in place if I can get it there. All right. Let's disengage the servo. So for the force test, what's going to happen is the servo is going to slowly press the arm against the anvil of this force gauge to try and find the point where it's meeting the anvil. And the purpose of that is that if we just slam the lever into the anvil like a hammer, then all of the force readings will be higher than they actually should be. And so what we do is we try and get it to just press up against it, release power, and then fully press against it as well. The other thing that is very interesting about stall torque on all the servos I tested so far is that they seem to stall in about 3 phases. In the first phase, they're applying a lot of current, a lot of power, and really reaching their maximum torque level. But that only lasts for about 3 to 5 seconds. After that, when it detects that it's stalled, it drastically reduces the current draw and the amount of force that is being applied while it's stalled. And then about 3 seconds after that, it reduces it again. And you'll see that here with the Axon servo. Because this test takes place pretty quickly, it takes place over about 10 seconds. I'm not going to be able to narrate it as fast as it goes, but you'll be able to see the narration in post-production when I put some of the notes on the screen. So let's go ahead and do the test. There, I was just getting the servo in the right position, and I kind of need to release it. So I'm gonna just back off and do it this way. So again, the first movement of the stall test is to try and probe for the spot that this is where it's just touching the anvil. Then it will release, and then it will do the actual stall test. So let's do that. So there's the probe, and then here's the release. and now is where it does the stall test. So it's doing the stall test. You can see the current, and it's currently pushing at about 34 and a half kilogram centimeters. I just took that number and multiplied by 5 in my head. Then you can see after a few seconds, it dropped down to be about 28 kilogram centimeters, and then it dropped down below that. So I'm expecting to put the text overlay on this to say what the different things were, but the end result that I get from this is that the stall torque that we had here was about 34 kilogram centimeters, which again is what Axon advertises on their website. So that's also a good confirmation about the testing system and the Axon servo that's there. The other thing that I'll note is that during that first phase, it was drawing quite a bit of amperage. And in that first phase, what I've noticed from all servos is they start with a very high current draw, and it slowly drops down for the first 3 to 5 seconds. And then once it gets past that first 3 to 5 seconds, it really drops, generally to under 2 amps for the remaining phases of the stall torque. What that means in terms of maximum current draw, as far as the first tech challenge rules go, I don't know. I don't know how servo manufacturers come up with their maximum amp draw, because clearly all the tests that I'm doing show amperages way above what the advertised max is. So I don't know if they do an average over a period of time. Maybe we'll get some clarification. One thing I have noticed is that there's not really I have not found a standard for how to test servos, and I've not found any manufacturers that do that. In fact, many of the people I've talked to about servo performance characteristics say that manufacturers vary widely in terms of what they report and how they report it, primarily because their market is not typically first tech challenge robotics, but hobby airplanes and drones and remote cars and things like that. And those have different selling characteristics than what we're looking for in First Tech Challenge. Anyway, that's been the test of the Axon Max Plus system, as well as an explanation of the servo testing environment. I hope you found it useful, and there will be more servo testing videos on their way.